Hi everyone, my name is Anvita Bansal and we are back with another lecture based on bit manipulation. So we are going to discuss this problem. Check whether kth bit is set or not. So in your SDE sheet, if you go to bit manipulation topic, you will find a problem like this. So let's see what we can do in this question. Let me just take this off. Okay. So you are given a number n and a bit number k. Check if kth index bit of n is set or not. A bit is called set if it is 1. Position of set bit 1 should be index starting from 0. So let's see what this problem is expecting us to do. So let's have some examples. Let's take this where we have n as 4 and k as 2. So we have to find for 4 in binary representation of 4, do we have 1 at second index of n starting from leftmost position? So let's see, your n is 4, right? And your k given is 2. So you have to check if binary representation of 4 has 1 at kth index or not. Okay, if it has, you return true, otherwise you return false. That's the question. Let me just check if you guys are able to see my screen. Why not? Am I seeing 20? Okay, I think I'm seeing the wrong one. This is the one which is live. Fine. Okay, so moving on to our problem. This is your number 4. Binary representation of 4 is what? Again, when we are solving problems of bit manipulation, we are actually playing with the binary representation of a given integer. Mind this thing that we are not actually converting the number, because in programs, in computer language, anything that we feed as integer or whatsoever, computer language or itself converts it into binary, operates on the binary forms of these numbers and returns us the answer in the format in which we have fed the input, correct? So we don't have to worry about converting it. So first of all, let's discuss the naive approach. What can be the brute force approach? Tell me. So the brute force approach can be, you convert n to binary form, n to binary, and store it in some number or string or whatsoever you want. Okay, so first I will convert n into its binary, that is 100, and then I store this 100 into some storage, and then I iterate over this 100 bit by bit and check if zeroth index has, this is your zeroth index, this is first index, this is second index, and they have asked for k equal to 2. So for every bit, in my iteration I will check what is the value of each bit. If when my k is 2, or when in my iteration I reach at index 2, I will ask what is the bit. If it is 1, I return true. But this is an expensive task, means in terms of time and storage we can improve it. So in order to improve it, we will use some bit manipulations. And what will be that? It is going to be very easy. If you all went through yesterday's lecture, then this is going to be really easy for you all. Okay, so binary representation of 4 is 100, 100. Okay, and rest of the bits can be set to 0 depending upon our requirement. Now what is first one method can be, what can you think of? See, I just have to check for index 2, right, starting from leftmost rightmost position. So you have to move in this way. Okay, so when you travel this way, this is index 0, this is index 1, this is index 2. So you have to check if index 2 has 1 in the binary form of this given number. So what can I possibly do? See, just think, if let's say I try to do its bitwise and with some number which is 1 here, which has 1 at this position, that is the most significant position is 1 and rest of them are 0. Then if I do bitwise AND of this number with this number, I will get 1 only and only if this index has 1 in my given number, right? This is just one thing, one hit and trial way that I am suggesting, and we can solve this. But the point is, what can we do to create such a number? So why not think of something like, we have 1, right? We have an integer 1 whose binary representation is also 1. So if I want to represent it in binary, I can write 1 as what? 0, 0, 0, 0, 1. Okay. Now if I do left shift on 1, by left shift, what do I mean? By left shift, I mean that actually when we do right shift, logically what we are doing, we are multiplying that number by 2 if I am doing right shift by 1, right? So when I am doing left shift by 1, I am basically removing the character from the leftmost index, that is this most significant bit gets removed and you shift number by 1 position to the left. So your number becomes like this, right? Do it one more time. I'll tell you why we are doing so. Then it becomes, you remove this character and the entire number shifts by 1 position. So your number will become like this. Do it one more time. Wait, your k given was 2. So I will do this, I will perform this left shift on that number 1 by only 2 times. So once when I did, I got this. Second time when I did, I got this. Okay. Now try to do its bitwise AND with the number which was your original number. So if I do bitwise AND with the original number, what will I find? See, your original number was what? 100, correct? So do you realize one thing? When I do bitwise AND, I am going to get 1. What was the idea of doing this? What was the intuition? So the intuition or the idea behind this was, when I took a number, your x is 1, okay? I am doing left shift on 1, left shift 1 by k positions, by k, okay, k times. Why am I doing so? Because 1 can be represented as 0, 0, 0, 1, no matter how many times you write 0. So if I get at kth index, if I get this 1 somehow, so whatever my actual number will be, its kth position, the numbers kth position, whatever it is, let's say this is your kth index, this is your kth index, it can be either 0 or it can be 1. So I am trying to create a number from here such that at kth index I have 1 always, so that whenever I do bitwise AND of this 1, if I get a 0, that will clearly mean that my number at kth index contains a 0. And if I get a 1, that will clearly tell me that my number at kth index has 1, right? So this is my intuition. So what I am doing, I am just left shifting my number 1. How many times? K times. So even if you see it in this way, don't get confused, your indexing starts from 0. So let's say your number is 4. So what you had 100, right? Rest of the numbers can be taken as 0. This is for explanation. Now I am writing k here. This is k equal to 0, this is k equal to 1, this is k equal to 2. Now I have 1 which can be represented like this, okay? I want to create a number such that at kth index I get a 1 in this number, so that when I do bitwise AND of this and this, I can easily figure if kth index has 1 or 0. So for that I want to basically get a 1 at kth index only. 1, I should have a number. I want to find a number which contains set bit only at kth index. So to get that, I will, if k is equal to 2, right, that means 0, 1, 2 in terms of indexing, I will left shift my 1 by 2 positions. So if I left shift it by 2 positions, in first time 1 will come here and second time your 1 will go here. So I am finally going to get a number which will have set bit only at kth index. Rest of them will be non-set bits. Okay, so when you do bitwise AND of these two numbers, you can figure out if you get this number, you will only get the result as 1 only if kth index has set bit in original number, and 0 if it doesn't have set bit at kth index. So if it is 1, you return true, otherwise you return false. This is one way. Fine. So other way also, let me just discuss the second approach also. Very easy, very easy. So if I write the pseudocode, not pseudocode, the entire code, it can be simply written as, if let's say your input is n, right? So n bitwise and with 1 shifted left by how many times? K times, right? If this value is equal to if this value is equal to 0, you return false, else you return true, or vice versa. Or you can do like this, if it is not equal to 0, return true, otherwise you return false, right? So we can do this. Second approach is, again we are playing with the bits. This time what I am doing, let's say your 4 is 100, correct? Let me take some other number. So what is the other number you have? So let's take another number which is 500. Your n is 500, okay, and your k given to you is 3. So let's see what is the binary representation of 500. So you have this given in your one of the test cases. So 500 can be represented as 1 1 1 1. How many times? 1 2 3 4 5 times 1. Then you have 0, then you have 1 double 0. This is the binary representation of 5. So in my second method, what I am trying to do, I am basically trying to do bitwise. Let me show you, just a second. So what I'm trying to do, I want to find what is present at kth index. So your k is 0 1 2 3 4 5 6 7 8. Fine. So I will basically right shift my number by 2 positions. Why? So that right shift means removing the last 2 bits from your number and shifting the entire binary number by 2 positions to the right. So the value, the bit at kth index can be found at 0th index. So when I will do it's bitwise and with 1. How do you represent 1? You represent 1 like this. So I will find if this value will be set, that means the value at index 2, index 3, let's say if it is 0, I am going to get resultant 0. If it is 1, I am going to get a resultant 1. So I can figure out if I get result 0, that means the index at 3rd position in the original number n was 0. And if it is 1, I will get a resultant also 1. So let's see how can I convert it. So if I do a right shift your n by k positions, okay, k positions. So if you do so, what do you mean when you do, how do you represent a number when you do a right shift? So again I told you, right shifting any number by k times means you are multiplying that number by 2 to the power of k, right? So if when k was 1, that means you are shifting that number by, you are multiplying that number by 2. Now it is n into k to 2 to the power k is what mathematically right shift is in terms of actual mathematical operation. You are multiplying that number, let's say 500 is being multiplied by 2 to the power of 3, and then that is 8 5s of, so 40,000 is the number. So its binary representation is what we are going to get by removing the last 2 bits. So this is the number you are going to get. You will shift every bit by 2 positions. So the final number is 1. See the number from here now. 1 1 0 1 1 1 1 1. How many times? 5 times, and 2 more zeros are added here. Now you do its bitwise and with 1. So if you do bitwise and with 1, how do you represent 1? You represent 1 like this. and rest all 0 0 0. So it will be 1 only if you have the last set bits as 1 in your original number. Okay, so if I get a 1, that clearly means 0 1 2 3, third index. Actually I was checking for k equal to 2, so this is the number I found. If your k is equal to 3, this is how you're going to represent number. Remove the last 3 bits. So if you remove the last 3 bits, this is the number you're going to get. 0 1 4, 5 times 1 4 5, and 3 times 0 added, right? And then you do its bitwise and with 1, you will get 0, which means the bit at third position in your n was 0. That's pretty much about this problem. Let me see if you guys have any doubts. You can ask me in the chat. Okay, so let's see the code also. So by the first method, what was the first method? I am simply doing, let's say, int x is what? You were left shifting 1, right? So 1 left shifted how many times? K times. Then you return, then you ask if your n and x, okay, if this is equal to 1, you return true, otherwise you return false. Okay, so let's check. Let's submit it. What is the problem? Let me just check what is the issue. So we are, what it is, so we are left shifting 1 k times, and we are doing bitwise and. So n and x, if that is equal to 1, we're returning true. I think I am doing the right thing. What is the issue with it? Let's try to submit it now. If it is equal to what is the, this shouldn't be the issue. See the problem here. That was the issue. Okay, so if it is not equal to 0, we are returning true. What was the issue with 1? I want to check. I'm just checking that why was that failing. Okay, got it. Fine. So coming on to the next approach that I discussed. So the next approach is in which we were right shifting the number itself by k positions, right? And then we were doing bitwise and with 1. So bitwise and of n with 1, when you modified your n, you right shifted your n by k times, let's say that is your x, and then you are doing, let's check if we, right? So that's the second approach. So we are done with this question. If you have any doubts, you can ask me in the chat. Rest, we are done. Right, right, not equal to 0. So that's all. Let me know if you guys have any doubt. Otherwise, we will wrap it up. Fine then, see you all in the next lecture. That was all for today. Bye bye everyone. Take care.